Good day, I'm Dr. T and welcome to my office. Today I would like to talk about chemistry, a topic that's near and dear to my heart because of course I am a chemist. So when I talk about chemistry, quite often I and my colleagues will consider us the central science. Because chemistry is bridging the gap between the macroscopic world, the world of rocks and bugs and bears and people and stuff, and the subatomic world. The world of quarks and electrons and photons and things that are the very building blocks of matter itself. Now, as chemists, we get our name because we study chemicals, and chemicals are going to be anything made of atoms, and atoms make up everything. Therefore, we study everything. Hey, good job description. Okay, so let's jump into a little more of this atom stuff. The idea of the atom originates with the Greeks, although I'm always a little bit cautious to give them a little too much credit, because they were kind of guessing and, well, you know, enough monkeys on enough typewriters, and you do get Shakespeare, although the internet may have disproven that. The idea of the atom is that at a certain point, if you start cutting something up into smaller and smaller bits, at a certain point, those bits will be so small that you can't cut them and still have the same stuff left. Now, of course, the Greeks were thinking bread particles and rock particles and other things like that that we now know are not true. Our modern understanding of atoms really begins in the early 19th century with a gentleman by the name of John Dalton. One that you will notice lends his name to a unit. We actually really like this John Dalton guy. His idea of the atom is what we now call the billiard ball model. He takes that, okay, there are various substances, some of which we have known for quite some time to be elements, and some that we have called compounds. Compounds are substances that, by various means, you can break down into constituent components. These would be what we would call chemical reactions or chemical changes. You take a substance and you do something to it, it is no longer that substance, it's now new substances. This is, of course, opposed to a physical change where you simply just make it look different. You cut it apart, you melt it, it's still the same stuff, it's just in a different form. So compounds, you can do chemical changes on them and you can break them down into constituent parts. Elements are a constituent part of compounds that you can no longer chemically break down into subparts. They are as pure as you can get, you can't break them down any further. This was the ultimate problem with some of the lead into gold ideas. Lead is an element. You can't break it down into gold because there is no gold in lead unless you accidentally or intentionally threw some in there to, show off. So we have our two ideas, elements and compounds. John Dalton makes a couple of revelations on this one. One, compounds are actually always these fixed whole number ratios of elements. Almost like they are being built of subparticles, little tiny globs, that are of each element, and that these globs can't be subdivided, and hence the fact you always get these whole number ratios of these globs. And, well, we've already got this idea that's been floating around for a couple of thousand years of the atom, so John Dalton's like, hey, we got atoms. And he makes the assumption that is fairly reasonably correct that they are more or less hard spheres, what we call the billiard ball model. Billiard balls, by the way, for those not familiar with the game of billiards, it's basically pool. So in the United States, we usually play pool, where in the UK and other places it's called billiards. I assume there's some differences in rules. I have no idea. I can barely hit the balls. But moving on. Okay, so we have the billiard ball model of the atom. Each atom is its own thing. If I have an atom of lead, that is an atom of lead. They are all identical to all other atoms of lead. Later on we'll discover that that's not entirely true. They're pretty close, but they're not quite necessarily identical. And that you cannot change an atom of lead into an atom of anything else. Likewise, later we will find that there are ways around this, but not chemically. You have to bring in the physicists to do this. And thus we get the idea of the atom. This is actually controversial for around 100 years. At the dawn of the 19th century, you get John Dalton coming up with the idea of the atom. But it's not really solidified until Albert Einstein starts looking at the way small particles behave in solution and realizes that this weird zigzaggy motion that lots of very tiny particles like pollen grains will behave when they're floating on water or doing other similar things, called Brownian motion, indicates that the water must actually be made up of little tiny particles like, atoms. Oh, wow, that's kind of cool. Now, before I leave you thinking that compounds and elements are all there is, I should point out that very rarely do we run into something that is just an element or just a compound. These are what we call pure substances, and most of the time we encounter mixtures. And mixtures are exactly what you think they are. They are a mix of more than one compound or more than one element or both mixed together. And thus, yay, you've got a bunch of stuff. Unlike compounds where the atoms have to be in fixed whole number ratios, mixtures can be in any old ratio they want to be. Some mixtures don't really work that well in certain ratios and better in others, but in general they're not locked in. They can be in a variety of ratios. And you can separate mixtures without doing chemistry. You can do a physical change, one that doesn't change the very nature of the substance, the way the atoms are attached to each other, but instead just changes their form into a way that they're now separate. So if you had a pile of salt and sand, one could, if one really wanted to, use a magnifying glass and a pair of tweezers and separate out the two. Or if one actually, had a life, you could dissolve the salt in water, which has not changed the salt, it has merely changed its form. It's made a new mixture, and then dry the sand and boil off the water for the salt, and boom, they're now separate. Whereas if this was a compound, you couldn't do that without fundamentally changing what it was. Mixtures come in two predominant flavors, or two predominant types. Now I should point out that nature does not classify things. We classify things, and nature is not beholden to our classification. So there are things that don't fit neatly into the boxes because nature doesn't care about our boxes. But the two boxes we have for mixtures that work pretty good are the homogeneous and heterogeneous mixtures. Homo means same, geneous means stuff. So a homogeneous mixture looks like one stuff. The example, of course, would be something like salt water or tap water. It's loaded with weird things into it. The heterogeneous, hetero means different, and genus once again still means stuff, is going to look like it is comprised of two different things. The classic example would of course be something like spaghetti. You've got the noodles, you've got the pasta sauce, you may or may not have the meatballs. They're mixed together, but they're in their own discrete pockets. All of the meat is clumped together in the meatball. The pasta is floating around and you've got the sauce going in and out between it, but you can clearly distinguish that you've got pasta sauce, and a meatball or several. And thus it is a heterogeneous mixture. Once again, there are things that kind of really border on the line, such as, milk. It looks like one thing, but it also, if you zoom in, doesn't look like one thing. It's what we call a colloid. So with that said, have a wonderful day.